fiber. It will be very expensive and will also take a lot of time to get it into the network, even if a lot of it is already on net. Also for the optical light system, it will be very challenging. Very simply because you have only a 10-year technology cycle, and if you want to do any changes, any introduction of, for example, a new core branch in your network, you have to take into account that it will take you approximately 3 months. And also the expenditure can be quite, well, sort of medium expensive to correct any bandwidth imbalance. Regarding the transponders, a little bit of a shorter innovation cycle, and therefore it's quite, well, it could be quite easy to introduce new transport capacity in the network. If time and planning permits, you can do that probably within a week. Transponders are not cheap, so also here you have a bit of a medium expense. You have a medium expense to make. So what I want to say in this slide is actually that having a right balance and trying to get these things introduced in your network in time can be quite challenging. On the other hand, we also have a few new technological developments. For example, actually it was high on my wish list, well documented and standardized optical line interfaces as well as control interfaces. Needed by my automation team quite desperately actually. And well, for the other items, it basically applies that what used to be sort of static resources in the network now have actually become dynamic and programmable resources. Especially the programmable OSNR margin that will actually allow you to keep a certain distance from the nonlinear Shannon limit is a very interesting one because it gives you the flexibility and the dynamicity in the network that you would like to have as an operator. So at SURFnet we actually want to follow the traffic because that's in terms of investments that you would make the most efficient. And well, if it turns out that this a balance is no longer exists, then it's actually not a problem to have this in the short term, because you can decide to make a little bit inefficient use of your capacity, of your installed resources. But on the long term, it would be very bad to do this. And if I look at our network, we see that traffic matrices can actually change quite rapidly. Especially now we see a lot of 5G possibilities on campus. We see a lot of customers getting traffic from Microsoft's Azure cloud. So it's mainly service popularity and geographic divergence, campus universities that open up dislocations to house their data and infrastructure. That will trigger new capacity and will put demands on the infrastructure and actually try to imbalance the amount of resources, infrastructure that we have and the bandwidth that we draw from it. So there's actually a very important need to assure that we have and that we can guarantee this balance, not only on the long term, but preferably also on the short term. And I have here a few examples why we would like to do this. Because in this example, you see, for example, that we do WSON to restore waves, to restore bandwidth in our network. And this is an example where we have, for example, a 100G wave, 50 GHz QPSK modulated between these two locations. And if we would have a failure there somehow, then the system would restore. So we have already some dynamicity in terms of routing and in terms of wavelength allocation. We can also take a different route, but the outcome of this WSON-based restoration is either it will restore or it won't restore. There's nothing in between. Well, in the next version of our transponder layer, we will have programmable transponders. So programmable transponders will, in this case, run on 200G, perhaps even at 400G. And well, normally they would operate, for example, with 37.5 gigahertz, making use of that FlexGrid feature in the network, and they would be using complex modulation at 16 QAM, for example. So now that we have restoration, and for example, in the previous example, if this particular route would not be supported anymore because of too bad OSNR, then we would have the possibility to scale down. We could go from 16 QAM back to 8 QAM. And also, in terms of the spectrum that we would use, we could sort of increase the symbol rate, and this way we would need a little bit more of bandwidth to still support this. And the other route could be a route that would also not exist with the same configuration as the original, perhaps not even with 8 QAM, and for this route we may have to go to QPSK again. And automatically going to QPSK means that for 200G you would need 75 gigahertz of bandwidth. So for 400G the same situation could apply, but that might even be the case that you cannot even run 400G on an alternative route in the network. If that would be the case, then we may have to decide to choose modulation format and symbol rate to, for example, achieve 300G, if that would be possible. That would not be ideal, of course, so it would be sort of a partial restoration. So this elastic and centralized control restoration provides us a lot of advantages. It's no longer a can restore or cannot restore. It has now become a actually partial restore and a way to leverage all the routing and wavelength tunability that we have in the network. So another example is capacity optimization. For example, in this link, which is nonlinear Gaussian noise constrained. So we have our Amsterdam one location to the left, Geneva to the right. So this link has just gone online actually. There are not yet services on it. We're still in the testing phase, optimization phase. It's mainly composed of G.655 fiber, which lacks dispersion. Dispersion is needed to make the transponders less sensitive to nonlinear Gaussian noise. And if you operate the link in this regime, then you actually want to have the longest, actually the most complex modulation and the most longest distances on the high wavelength, because that's where you have the most dispersion. And the worst performance you would actually see on the blue part of the spectrum, so the high frequency waves. So if we would take that, for example, in combination with our London-Amsterdam link, then we would have to do some clever wavelength planning. For example, if you would take a situation where you are looking at 8 QAM, 62.5 gigahertz signals, so typically it could be 200 gig, for example, then what we want to do is actually the short links will be mapped onto the bluest part of the C-band. So these are also short links, while for medium distances we would operate the waves a little bit more towards the red part of the spectrum, because there you would suffer less from nonlinearity. So these are also medium links. Then we would go to the long links, so also the long links like London, Paris, and Amsterdam, Geneva. Those would be typically mapped in this part of the spectrum. And of course the ultra long links will be mapped completely onto the right part, onto the red part of the spectrum, long wavelength. So this is just for 8 QAM, 62.5 gigahertz. If you would have different modulation formats, different bandwidth, of course this would change a little bit. And what's very interesting is that it also imposes a different view on spectrum sharing. So if you want to do spectrum sharing, you really need to know what actually is the content that's being transported in order to optimally use the fiber infrastructure that you have. So I think that also in the future, when you talk about spectrum sharing, this also will be a very dynamic service that will have to interact with the network management system of these links. So just to conclude, we think that a full elastic network with flexible restoration has several advantages. especially when you talk about the fiber layer. So we can actually use this technology to delay the investments in fiber, and we can actually use it to have a higher loading of our cross-border fibers. Together with the ability to program these interfaces, to have these configurable and adjustable, controllable interfaces, we can also continue to deploy restoration, even partial restoration. And very important is the fact that we can actually postpone the need for regeneration and postpone any topology impacting restorations, which is something that that my service layer colleagues are not very keen on doing. So I think that concludes my part of the presentation. So Jonathan, I would like to hand over the mic. So I think that's for you.
Thank you. Thank you very much, Rob. So I'm going to pick up where Rob left off and give a bit more of a framework for how all these things that Rob is talking about can be achieved. And if there's anything that I'd like you to go away with from today's presentation, it's understanding that the optical network today is not the optical network you grew up with. The optical network we all grew up with was a static network. We thought about the services traffic that it needed to carry. We then planned that network, we deployed it, and we really considered it to be in place for a long time with slow changes and migrations. The kind of optical network that we are really poised to deploy and use today is a programmable dynamic optical network, one that could play an equal partner in what eventually I think we're going to go to as an industry in terms of a multi-layer optimized network, where the services network and the optical network work hand in hand, both in terms of cost efficiency, in terms of providing the services to the end users, providing different types of service differentiation, particularly as we move towards 5G services, and providing advanced capabilities for restoration in the case of failures. So the kind of programmability that we have actually exists at multiple levels. This is a pointer over here. Thank you. We see, for instance, we have programmable line rates as well as programmable spectral grids. And as I'll explore in a bit more detail, this is a capability that gives us an ability to do programmable throughput, where we can really optimize the amount of capacity that we can carry over a particular channel. In terms of moving this capacity about, of course, we have wavelength routing, which is supported through programmable lambda routing. And we have programmable OTN switching. So in other words, you can do routing both at the optical layer as well as at the services layer. This is possible for speeding up provisioning, as well as giving you all sorts of capabilities for restoration, whether it's at the wavelength layer like WSON or at the services layer like ASON. This could be done in-band, or it could be done through a centralized SDN control framework. Of course, on top of that, there's the control mechanisms, which we see through this SDN control, which could be done by the purveyor of the network, or really, as we see the major trend taking place right now, it's being able to put this network together through multiple subsystems, each provided independently by different providers. And this is where you're really looking towards a disaggregated network and a need to support open interfaces on each of the subsystems. This is really taking place, this revolution, at multiple levels across the network. And I'm not going to read through this slide in detail because obviously it's too much detail. You could read through it when you get the conference proceedings. But the point I want to make is that the changes that are taking place from the way things used to be until now and going forward are really dramatic, both in terms of the client interfaces, the line interfaces, the ability to do routing and switching, the way that we're able to get information from the networks in terms of telemetry, the way we're able to control the network in terms of changing things on the fly, and of course, opening up these interfaces that people could put together the subsystems in a multiplicity of ways to really suit their particular needs. I think one of the more exciting things, for instance, is in the past, we had to have a strong relationship between the clients and the line interfaces. In terms of 10 gigabit Ethernet, went to 100 gigabit, 10 gigabit per second line interfaces, 100 gigabit Ethernet to 100 G line interfaces. But we see what's taking place is that the evolution is taking place separately today on the client side and on the line interface side. How do we deal with that? So we're getting multiple options. You can deal with this at the client side by using protocols such as flexible Ethernet, or you can use this on the line side by using new standards such as FlexO. So we're getting this kind of flexibility and the ability to control this flexibility dynamically that's really giving us the network of the future. Let's take a look at some of these examples in a bit more detail. Talking about programmable throughput. How did we used to optimize line capacity? In the past, it was very simple. We had at the most, if you like, 2 knobs, each of those with really just 2 ways to switch the knobs. You could choose between a line rate, say, of 100G or 200G, or you can choose between 50 or 100 gigahertz channel width. And you really didn't have the channel width capability because you really had a system which was fixed either for 50 gigahertz or 100 gigahertz. So really you were talking about a 50 gigahertz network with either 100 or 200G. Where we're going towards today in terms of a programmability is being able to actually move the line rate from steps from 50G all the way to 600G. At the same time, you can put this together with flex grid filters going, say, from 37.5 gigahertz all the way up to 100 gigahertz. When you combine these together also with a flexible baud rate, you're able to get continuous tuning, at least 70 hard options with multiple soft options in between, that really gives you the ability to pick the sweet spot to maximize the transmission over a particular channel based on the conditions of that channel. Look something like this, whereby you see a continuous modulation envelope going all the way from short reaches, which you can then provide 600G connectivity over, all the way up to ultra-long reaches, going for thousands of kilometers, say for submarine applications, where maybe you'll drop down to 50G services. The point is that really depending on the specifics of your network, you're able to fine-tune and pick the sweet spot all along this curve, doesn't point, all along this curve, so that you could operate really right at the edge of the nonlinear Shannon limit. And by doing that, what you're able to do is optimize the channel capacity. And at the same time, being able to have the flexibility to get other certain kind of value-added applications. Let's take a look at a few examples. So for instance, let's say we have 3 nodes, and there's 1 terabit of traffic between each of these nodes. In the old paradigm, because you're really just limited to 100 and 200G links, you might need, for instance, 25 links in terms of being able to satisfy that capacity. But under a programmable network where you have programmable throughput and you could fine-tune the links, so for instance, the 200G links you can probably push up to 350G. The 100G link maybe to 200G, and the 100G link another one because it's longer to 100G. What you're able to do is bring that traffic down to 15 links. This is a huge savings in terms of the number of transponders that you need. So immediately it brings you savings. But it can do much more than that. Let's take a look at what happens under failures. And Rob gave one of these examples in his presentation. This is looking at it from a slightly different way. Let's say you have a customer with 3 100 gigabit Ethernet services, and you're providing that today over a 300G link at 75 gigahertz. The link fails. You can't find another link at 75 gigahertz. But you can route it through a ROADM. And what you need to do, however, is increase the bandwidth to support the 300G link because it's more distance to 87.5 gigahertz. This is something you can now start to do dynamically, and you can recover the service. And moreover, if you're starting to have ability to communicate with the client side, let's say you can only find 200G. You can now, if you're using something like a Flexi interface, you can command the client side to subrate so that their service is diminished, but it continues and it survives. This is the kind of things you can do with a programmable network. Another example is truly getting bandwidth on demand kind of services. As an example, let's say you're a user and you're connecting to your data center, and most of the time you just need 100G connectivity. But in the future, or maybe under certain circumstances, when you're really doing a lot of backups, you want to increase this to 300G. So what you do is you buy a service where you have 3 physical interfaces, because you need the physical interfaces for 3 100 gigabit Ethernet services, but you're just paying most of the time for the 100G connectivity. When you need the additional bandwidth through a customer network management interface, you just dial it up and say, give me the additional bandwidth for these physical interfaces. It's not necessarily guaranteed, but as long as the service provider can provide this on a best effort basis, you will get this most of the time. This is the way, by the way, we get our computer services today from places like Azure or Amazon Web Services, based on just being able to dial up the additional computing capacity, translate this to bandwidth capacity as needed. Again, something we can now do with a programmable network. Probably the most exciting thing, as far as I'm concerned, and I'd put this a little bit in the realm of future application, because it really requires a different mindset in terms of arriving at this kind of application, is how we deal with filling up our networks. Today, when we build our networks, we build in 3 to 5 dB of margin. Why? Because we're concerned that our networks are going to degrade over time, and as they degrade over time, the capacity won't be there. The OSNR performance won't be there, so we build in this capacity. Just-in-time provisioning. When you're building a car today, you don't get your parts for the car and have them sit in the warehouse for months. You get the parts for the car 1 or 2 days before you need to build it. We can start to apply the same kind of mentality when it comes to optical networks, whereby you can start provisioning your networks, say maybe with only 1 dB of margin. And then as things start to degrade over time, what you can start to do is dynamically shift the resources around. What this does is it gives you a huge ability from day one to actually get much more value out of your CapEx investment in your network. It's a different kind of mindset, but it's one that really is feasible to do going forward. Finally, I just want to emphasize a few points. We talked about openness. This is something which we see that you as an NREN should be able to piece together yourself from multiple piece parts. Whether you're putting together an open line system, an open transponder system, or an open OTN switching system, there are standardized interfaces that are being developed by a number of industry forums, and this is something as a direction that we strongly support at ECI, that you can put together this programmable network from different subsystems, from different providers. And I will leave you at that, our little pitch for Apollo networking. We provide a programmable network that really enables you to maximize the capacity and responsiveness of your network, and one that's open, that you can choose to put it together with pieces from ECI or from other parties as you see fit. And I think I finished with about 5 minutes to go for questions, if there are any. Rob, if you'd like to join me.
Okay, any questions that we can take?
Hi. Yes. Could we put the slides back up? I know the one you mean.
It's wonderful to start using all your capacity when you start, but then you had an explanation that when that network starts to degrade, that you could repurpose something, and I wasn't clear as to what, to keep going.
So what you can do is repurpose the fact that there's some still additional margin in other parts of the network. So what you can start doing is moving some of the capacity that is taking place within channels that all of a sudden are being used up to their ultimate maximum into channels where there's still some capacity. At some stage, of course, all your capacity gets used up. Think about it again from a computer paradigm. What you need to do then is put in a new computer shelf. Over here, you would have to now provision, say, a new transponder pair. But again, what you're doing is you're provisioning these new transponder pairs in response to the fact that you're beginning to use up your capacity, as opposed to just because, there's a brand new traffic demand.
Hello. In your your slide number 14, you said that if one link goes down, then there is alternate path, your traffic can be moved, right? But then you need to reprogram the switches and underneath hardware, right? So how do we deal with some of the packet losses happens because of that movement of channel from one to another?
Okay, I think that's.
Because it's a programmable
I think
network,
I understand
right?
the question. Yeah. So the question is basically, how do you deal with packet loss if the network is in the restoration phase?
Yeah, when you
Yeah.
switch from one port to
Yeah,
another port, or one channel to another.
Yeah,
channel.
exactly. Of course, restoration is not intended to, to solve a fiber break without any outage whatsoever. So on top of this transport network, there is a service layer network. In our SURFnet is currently being rolled out, composed of all Juniper MX platforms, and they will actually take care that you have protection on the services. Of course, we need to implement bandwidth for that. So the net effect of protecting these services will be that for a particular time, the load on the interfaces will be high. So for example, internet kind of service, customers will probably feel like it feels a little bit sluggish. And then after a minute max, then the restoration kicks in, providing enough bandwidth to bring that fast and quick internet back to the user. That's the concept. Yeah, good question.
Thank you. Thank you for presentation. Just a question to Rob regarding this quality of different part of your spectrum. You said that the lower bandwidth or wavelengths have lower quality. When you transfer it or translate it to dB on USNR, how many dBs differences between the lower and higher wavelengths range? The first question, the other question is it a matter of, it could vary from vendor to vendor? Is it not a matter of the quality of amplifier you have and the flatness of gain actually the amplifier delivers?
No, it's mainly contributed to the lack of dispersion. So if you have the same launch power per channel on every wavelength, then you will see a worse OSNR on the blue part, simply because you have less dispersion there compared to the red part. So if you want to solve that, you cannot solve it by increasing power. You might even have better performance by lowering the power, because you have on the blue part less nonlinear interaction. But if you start lowering the power, then of course you pay for the OSNR penalty directly at the red part of the spectrum. So there will be a balance. And some initial tests that we did, it could easily be up to 3 dB.
Up to 3 dB,
It can
okay.
be quite high. Yeah.
I thought dispersion DC actually will be taken care of DSP, but it's not. Okay.
No, this is not dispersion. Of course, the dispersion is compensated by the DSP, but this is about the nonlinear noise that originates from the Kerr fiber nonlinearity. That's the reason. Yeah, and of course, to some extent, it can be solved by your FEC engine, but there are of course limitations. No.
Any more questions? Thank you for an excellent presentation. Thank you.